we studied mobility of free electrons, holes, and diffusion constant of holes and free electrons, and observed that mobility of free electrons and holes are the parameters which defines the drift current density, and diffusion constant of holes and free electrons are the parameters which define the diffusion current density. Also, for approximately all the semiconductors, we can observe that the diffusion constant and mobility of free electrons is greater than as compared to holes, meaning that free electrons are more mobile, creating higher current values for same electric field or concentration gradient values. These concepts are good for theoretical understanding of the flow of current if electrons and holes are independent, but practically it is not the case. As already told in the last lecture, semiconductor devices operate due to excess holes and free electrons which are created by bringing the semiconductor in non-equilibrium condition. And these excess holes and free electrons do not move independently of each other, but they diffuse and drift with the same effective mobility and the same effective diffusion constant. This particular phenomena is called ambipolar transport. In this lecture and the next few lectures, we will focus on the behavior of these excess carriers and will derive the expression for effective diffusion constant and effective mobility. We are going to develop the continuity equation for excess carriers in this lecture. Consider an elementary volumetric cube with whole particle flux density Fx at the left end and flux density Fx plus delta x at the right end. We are considering the motion of hole in only x direction. The flux density Fx is the number of particles crossing per unit area per second. And also we can write that Q into Fx is nothing but the current density, as if we multiply the charge with the number of particles flowing per unit area per second will give us nothing but the current density. We can rearrange it like this and let this equation V1. We will be using this equation later. The whole purpose of continuity equation is to find the rate of change of hole concentration in this elementary volume which we have considered. Now, we can say that flux density at the left end minus flux density at the right end is the amount of holes that remain in the cube. Or we can say that it is the buildup of hole per unit area per second. And if we divide it by delta x, then we can say that this represents the buildup of hole per unit volume per second. Or we can simply say it is the rate at which holes are building up inside this elementary cube per unit volume per second. If we have to include the generation rate and recombination rate, then for the rate of buildup of hole in the elementary volume, we can write here for the expression for net rate of holes building up inside a semiconductor, we have three terms. This factor comes because of difference in number of incoming and outgoing hole concentration. This term represents the thermal generation rate, and the last factor is the recombination rate, which you have studied in the last lecture. You can remember this as an analogy like assume that we have an island in which there are no humans, but after being discovered, slowly more and more number of people are being transferred here for establishing a new settlement. But obviously, if there are 10 people and 8 will remain here, then 2 will go with the vote to bring back more number of people. But obviously, these 8 humans are not immortal. As the time will pass, few of them will die, and it may be possible that a new child is also born, which will eventually fluctuate the population of human density. You can assume that the incoming influx of people can be assumed to be fx, and the outgoing influx can be assumed to be fx plus delta x, and generation rate can be assumed to be birth rate. Similarly, recombination rate can be assumed to be death rate. Now, if we put delta x to be approaching to 0, then we will get here tau pt is the total lifetime, which includes thermal equilibrium carrier lifetime and the excess carrier lifetime. We came to this equation because we know that differentiation of function x with respect to x can be written as now. If we put the equation first, which relates the flux density with current density into the continuity equation, then we will get this is the final equation which you have to learn by all means. And remember that Q is the charge on the particle. So it will be plus Q for hole and minus Q for free electron. Now, if we want this equation to extend further, then we can write current density due to holes to be equal to now. If we put the value of current density due to holes in the continuity equation, then we will get this is the continuity equation for holes in expanded form. This is very important. Similarly, if we want to find continuity equation for free electron, first we have to put fx to be equal to jx divided by minus q, as the charge on a free electron is minus q, and after that all the procedure is same. We will get the continuity equation for free electron to be equal to I hope all the steps are clear to you. We will see different possible cases of this particular equation in the next lecture, and will discuss a very important case.